Okay, so this is a short little video here about the motion of a wave. Um, if you look at the little diagram that I have shown here, I'm giving you some basic vocabulary that you should know about a wave. First things first, just parts of a wave. Any peak like this is called a crest. Anything down at the bottom here is called a trough. Okay, the distance between our equilibrium point down the middle and either a peak or a trough, no matter what, I could draw that either way here. Okay, this is known as the amplitude. Okay, and then anywhere from peak to peak or trough to trough, or even if I started here and went until we repeated, and that is known as the wavelength, which gets the symbol lambda measured in meters. Okay, so the definition down here for wavelength, or lambda, is the distance between two successive crests. And of course, you could also give it, any of the other ones, troughs, or from just any time where it repeats itself. Okay. Another term that we're going to learn about here is wave velocity, which is actually the velocity at which those crests move. Okay. And I've given you the basic formula. The velocity, because velocity is in meters per second, we've got a wavelength in meters divided by a period in time. That would give us the velocity of that particular wave. However, a more common version of this equation is v equals lambda times f. Because we know that frequency and period are inversely related, we can make that substitution to get velocity as wavelength times frequency. Okay. Something else, though, objects or objects that have a wave in them, like today we used a spring or a slinky. The wave velocity does depend on the medium in which the wave is traveling through. So if we had taken one of those springs or one of those slinkies and we had stretched them, to a much greater degree, the tension in that string or spring actually matters. Okay. Also, how heavy that particular spring is, or the mass of the spring, and how long it is. All those things do affect the velocity of the wave, and this is the relationship. Velocity then is equal to the square root of the tension divided by the mass divided by the length. Now, this bottom number here is often just referred to in problems as the mass per unit length. So be aware that when they give you a number, they might say mass per unit length, and there's only one number that you have to put on the bottom. So what this ultimately means is if we have a greater tension, it's going to go faster. But if the material has a larger mass per unit length, if it's heftier, we're going to reduce the velocity, which makes sense because if you have more mass, it takes a lot more to get you going. Okay, therefore more inertia and a smaller velocity would require more force to get you moving. Okay, so that's just a little bit about wave motion. Obviously, we'll start doing some problems in class tomorrow.